Assalamualaikum warahmatullahi wabarakatuh. We are going to explain about application of differentiation, which is related rate for MAT 183. I am going to introduce myself and my team members. My name is Khairil Danish Irfan bin Haidar Azam. My team members are Muhammad Khairi Danish bin Hamzam and Muhammad Aimanuddin bin Azaman. We are from Group A4 AS 120-18 from UITM Tapa. Now, I'm gonna talk about what topic we're gonna learn in application of differentiation. First is related rate. Second is analysis of function 1, which is increase, decrease, and concavity. Third is analysis of function 2, which is relative extreme, first and second derivative test. Fourth is maximum and minimum problem. And lastly is rule theorem and mean value theorem. The agenda we're gonna talk about this presentation is first, what is related rate? Second, why we use related rates? And third is problem statement for related rate, and fourth is the solution. Let's say we are inflating a balloon, and let's pretend the balloon is a perfect sphere. So we have a sphere that is expanding at a constant rate. Now, say we want to describe the rate which the volume of sphere is increasing, as well as the radius of the sphere is increasing too. Both of these values are increasing due to expanding of balloons, and their rate is increasing are related, hence related rate. But one of these probably much easier than others. So rather than measure both, let's measure one that we can and compute the rates. Then, why we use related rates? First, related rates come in handy when we have two related quantities and one of their rates of change is much harder to find than the other one. Second is, related rates help us determine how fast or how slow a certain quantity is changing using the rate of change of the second quantity. Now, I'm going to tell about step to solving related rates problem. First is draw a diagram if possible. Second is label of the quantities mentioned in question. Third is find in the question that relate the quantities whose rate of change in to be found to quantities whose rate of change are known. Fourth is use the chain rule or implicit to differentiate both sides of the equation with respect to time. And lastly, solve the derivative that will give to the unknown rate of change.
The question is, a farmer has 200 meters of fencing and wants to enclose a rectangular that maximizes the enclosed area. We have two sub-questions, which is question A and question B. The first question is, show that the area is A is equal to 100W minus W squared. So, I have made a problem statement for the question A. I will show you a step-by-step to find the answer. I made for a 5 step to get the answer. So, the first step is, define the variable. We can let L to be length of rectangle, and we can let W to be width of rectangle. So, second step is, write down the constraint. The perimeter of the rectangle is given by the equation 2 bracket L plus W close bracket and equal to 200, representing the total length of the fencing. So, the third step is express the quantity of to be optimized. The area of rectangle A is given by the equation A is equal to L multiplied with W. Step 4 is solve the constraint equation for one variable from the perimeter equation. Solve for L in terms of W. 2 in a bracket L plus W is equal to 200. We need to divide 200 with 2 and we will get the 100 is equal to L plus W. We put L as a subject and we change the position of W and it will be L is equal to 100 minus W. So, the last step is substitute the expression for L into the equation for the area A is equal to L multiplied with W. We substitute the L value is 100 minus W and we need to solve the equation and we will get A is equal to 100 W minus W squared.
And now we move to the next question. B. What are the dimensions of the rectangle that maximize the enclosed area? Solution is first step, we need to find the derivative of the area with respect to the width. We got the area over the width equal to 100 minus 2W. They are the first step. Second step, set the derivative equal to 0 and solve for the critical point. We got here 100 minus 2W equal to 0. 2W minus 2W equal to 0 equal to 100. So that we got W equal to 15. Step 3. Substitute the value of W back into the equation for L. L equal to 100. For this case, we just replace the value of W into the equation. We got here L equal to 100 minus W. So we replace the W value that we got at the second step. There. In the equation, L equal to 100 minus W. So we replace the W equal to 50. So we got L equal to 100 minus 50. And here we got L equal to 50. Step 4. Check for the maximum. To confirm that this is the maximum, you can check the second derivative or observe that the area increase on both sides of critical point. Step 5, or on the last step, step 5. Write the final answer so that the dimension that maximize the enclosed area are length of 50 meters and a width of 50 meters. So we know that the enclosed area, the maximum enclosed area is 2,500 meters squared. Is that?
In conclusion, we must take dy over dt out when we're doing related rates question, and we can use application of chain rule technique. Lastly, in application of differentiation, we also learn about maximum and minimum problem that we can relate in situation like a container in the shape of a right circular cylinder with no top has surface area 3 pi feet squared. What height and base radius will maximize the volume of the cylinder?